Hello and welcome back. Okay, so today I want to build the memory bridge which connects the main bus and the memory data bus. Okay, so a quick reminder of what the memory bridge is. This is my bus outline of the 8-bit buses from part 13. So we've done quite a lot of this now, the ALU and the general purpose registers. The transfer register is our primary special purpose. The constant register is connected to both the main bus and the memory data bus. We've got a direct connection from the memory data bus to the fetch unit. So all of this has been done. The increments and decrements are slightly different than I wrote down here, but on this the only thing we're really missing is some I/O and the memory bridge. And the memory bridge is a two-directional link between these two buses. Okay, before I go on, I do want to correct one small mistake. When I was wiring in the temporary lower half of the transfer register, I did say there was no spare connection to connect the address bus output, and of course in hindsight I could have just done this. So we've got that connected now, and then I just wire in the assert line and that should be okay. Now let's see if we can write a bit of test code. Right, so we've got memory read instructions in. Now we don't have any RAM, but I'd like to add the memory write instructions because we can at least test what the bus lines are doing. Right, so let's load A through TX. Now let's load C and load D through SI. I'm just trying to load from two sequential addresses there. And then we will attempt to store A and B at those two addresses. Won't work, but we should see the data come onto the bus and see the control lines activate. I've defined these two values up at address 128 and loaded that into TL, which is TX for all intents and purposes at the moment. Load 1 and 2 into A and B, clear C and D, don't really need that, but then we're going to load C from the address of TX, so that should become 128 if it's all working, and D from the address of SI, which is TX incremented by 1. We need to do that cycle earlier. If the memory bridge is done and working, C and D should become equal to 128 and 130. And then we should see 1 and 2 appear on the memory data bus when we do the memory writes. We haven't got a RAM chip or the extra circuitry, but yeah, that should be a good test. So as the 128 and 130 appeared down at address 128. So I'm quite relieved because I had never tested that piece of functionality in the assembler. So now we need to add the memory writes in. So these are going to be very close to a copy of the memory reads. So the address we're outputting is the same. We want to assert the relevant registers and load from the mem bridge. Really should do load and assert, or memory read and memory write versions for TL and TH as well, but doesn't really impact us today. Right, so it should be program ROM and pipeline 2A I need to update. Okay, now I had to do a bunch of diagnosis then. There's been some wires and stuff come loose moving this board around, but I've got everything running again. I need to make some room. Now what I'm interested in is the memory control lines here, assert, load, and the one I'm calling direction. Okay, so this is our load TL, 128. Good. Now we clear C and D. And then we've got move SI, TX. Yeah, so we've got gunk in the upper part still. Increment SI, happen there. Now the important bit. We're going to load C from the address of TX. Now this isn't going to work. Should have chosen a register rather than TX, but we should see an assert, so this light should go out. Good. And now we're going to move D, SI, so we should see the assert to bus line. Then we store A into the address of TX, so this time we should be seeing the load go low for half the cycle and the direction line go off completely when the instruction gets up to the top. Yes, so that's good. Okay, that's behaving itself. Now we need to build a memory bridge. Okay, now let's have a think about what the memory bridge needs to be. So on the left here we've got the memory data bus, and on the right we've got the main bus. Now we've got two lines coming in, one is assert and one is direction. I've not put the load line on here because it doesn't actually relate to the memory bridge. The load is going to be used to trigger the memory write operation. If all these terms seem back to front, it's because the load and assert are using the same terminology as we use for other devices on the bus. So when a register loads, it's taking the value from the bus into the register. So when the memory bridge loads, it's taking the value from the bus and sticking it into whatever address is currently selected in memory. So it kind of seems inverted from the memory bridge, but I think it's better to keep the terminology there. Think about what the lines are doing. So for a read, what we're actually doing is telling the memory bridge to put the contents of the memory data bus onto the main bus, so that's an assert to bus operation, so the assert line goes low. For a memory write, we get a load line like we do for a register, but I've added this direction line because I figured we'd need it. Now what the direction line is, it's basically the same signal as load, but we're not ORing that with the inverted clock. So it tells us for the entire duration of the cycle that the direction of data travel is from the bus into the memory data. So we have a two-way operation. During a memory read, we want to take whatever's on memory data and put it onto the main bus, and during memory write we want to do the opposite way. And so the first thing I looked at was this 74LS645. Now this is kind of similar to the 74LS541s that we've looked at before. So 645, this works similar to the other line drivers, but we've got this direction control and we've got an enable line. Now the enable is active low. So I mean, this looks ideally designed. So it connects two buses and the direction line determines which direction the data is going to travel, and the enable line turns it on. So direction line goes where we want, and assert is going to end up being the ANDed together version of these two lines. So if either assert or direction is low, we want to switch the transceiver on and then direction points the way. I'm pretty sure that would work, but I think there is a minor flaw to it. Now this AND gate takes time. Every single other assert is either a 574 or a 541 wired directly to the output from the 3 to 8 line decoder. And so we can be pretty sure that we're not going to see contention on the main bus, because those lines, there's only ever one that's low at a time. But if we stick this AND gate here, I'm a little bit worried about the time delay on the AND gate. This may be nothing for me to worry about, but I'm kind of paranoid about these things at the moment. So what could happen here is the enable here comes on very slightly late, and then it will stay on very slightly late as well. So it's possible that this will be asserting to the main bus for a tiny fraction of a clock cycle while another device is asserting. So I wanted to look at other ways I could do it where I would be more confident that's not going to happen. So 74LS541. So this will enable us to do a memory read quite easily. Take our assert line, connect it to the enable just like we have for the registers, and yeah, I see that working. Now to go the other way, we just add another one. I've drawn it upside down because we're obviously connecting the inputs and the outputs on opposite sides here, and then our previous direction line operates as the assert in the other direction. Now you can probably guess from just the naming of the direction line that I was thinking for a while along the lines of the other approach, but this should produce the same result, but it doesn't have the timing concern on this. So this is what I'm going to build. Okay, I need to get these memory data bus lines out of the way temporarily. Now I'm going to make it so that the upper side of this is the memory data bus, and then the lower side is the main bus. Let's do it the other way. Right, so the first data line is there. I'm going to position these chips to match these green wires I've got. So that should work. Power, ground. Be a bit more careful on this side. Right, so this is going from memory data bus to the main bus, so this needs to come from assert. And this is the one that comes from direction. Then the other enable lines need to be brought low. Wrong, that's the enable input, and this over here is the second enable input. This is going to be a very tight squeeze again. Hopefully that gives us good connections, but obviously relying on the connections going across here to bridge these two sections of wire. Okay, I'm going to give that quick test just to confirm the wires are still connected right. That's behaving itself. Okay, so now this side is effectively the main bus over here. I'm really tempted to make up some little mini PCBs for making all these connections. Main bus. I'm going to swap these over so I can use the longer cable where it matters. Now I think the memory bridge should work so far as reading now. Okay, so now you should be seeing the move C, TX. So we should be seeing the assert line drop low. So in that 128 is on the bus and is into C. So then it was 130 in the next address, which is what's being pointed to by SI. There, it's worked. Excellent. The next instruction about to get loaded in is the move TX, A. And that's a problem in and of itself because that will drop the direction line this circuit in the memory bridge will reverse itself and it will start pulling what's on the main bus and pushing it onto the memory data bus that the memory chip is going to be also contending with, which would be bad. So we need to do something about that. Now at the moment, memory is one of these. It's a 28C16. The wiring on these is very similar to the RAM chips though, apart from the fact that the actual process and the frequency with which you want to write is different. A lot of the other functions of the chip are equivalent. We've got the chip enable line and we've got the output enable line. So this line here is output enable. So if we bring it low, we're reading from memory. So we're seeing the 1 here, we're seeing it in the fetch unit. If I bring that line low, it goes away. Now if you think about the direction line here, when that goes off is when we're trying to assert something onto memory data. And so this output enable line needs to be the opposite of that direction line. So this is our old friend 74LS04. And I'm going to chuck one of these in here for now. I need to use some of this space for a circuit later on, but for now that can go there. So I've taken the direction line and I pass it inverted into the output enable line of the ROM chip. Right, go through this all again. So it's the load A, B, TL, clear out C and D. I'm going to move TX into SI, increment SI, but clock it twice to get that. And now we're going to move C from the address of TX, you get the 128, and then the 130 from the address of SI. And now the move TX, A is coming up. I won't do anything till it gets to here, but A is 1 and the address of TX is 128. So if it works, we'll just see the lower LED. If it doesn't work at all, we'll see the upper LED because it's the 128 that's being read. And if we see them both come on, we turn it all off quickly before something dies. Okay, see assert to main on B. So we've got getting the correct response. So this address, writing B, what happened to, so that's the move SI, B. What happened to the move TX, A? I must have skipped over it. At the end of the day though, that is working. We've got a functional memory bridge. Okay, so I got to the edit process and I didn't want to leave that missed memory write unaccounted for. So let's have a look at that again. So that's the inc SI. Those are the 2 memory reads. And then we should have 2 memory writes. And we only get the second one. So that's the write B to the address of SI. Okay, look at that again. Right, so this should be reading into C from the address of TX. I think I saw what happened there. Right. Watch the program counter. This incremented, but we didn't see the increment light come on. And we didn't see that because the bus request line is set, which comes all the way down here, which causes the fetch to emit a NOP, but it also sets this line high, which is what's supposed to stop the program counter from incrementing. So that is where we've skipped over the load from the address of TX. So then once those memory writes, or memory reads, sorry, are done, when those memory reads are done, the next instruction is the write to the address of SI. So our memory bridge is working correctly, but the circuitry for bus request isn't correctly suppressing the increment of the program counter. Let's have a look. Now all the other control lines that go over here go directly, but that one, after we got it working, we added the OR gate to OR it with the reset signal for inside the reset handling circuitry. So let's undo that change. So this should be the mov c, tx, and the increment hasn't happened. So there is our mov address of tx, a, so our memory write of a. So we're getting a out, and then the write of b to the address of si. Okay, well that's cool. We've definitely proved that the memory bridge is working right, but this is slightly worrying. Also goes to show that I should be checking all the functionality when I modify a piece of circuit like this. So we've obviously got just that tiny amount of delay on the signal is enough to make the program counter increment not behave quite correctly. So I want to investigate that a little bit further in the future, but I think we've done enough today. Well, I very much hope you found this interesting. I'm certainly pleased that we've got this going. Still feels like this is a little bit messy, although once the transfer register is on the new PCB, I'm going to build the new memory over here, and a lot of its wires are a lot closer, so I'm hoping that will be a bit cleaner. And this is all a little bit messy down here as it is anyway. Okay, thanks very much for watching. Hope you enjoyed. Goodbye.